All right, in this video, we are going to work through our first example involving numerical limits. So before we get to the actual work itself, let's take a look at the informal definition of limit. The formal definition is a complicated definition. So for our class, we are going to just take a look at this informal definition to kind of just get the idea of what this means to say this, that the limit as x goes to a of f of x is some number L. All right, so the informal definition says, suppose I have a function f and its domain is contains an open interval around the number a except possibly a itself. So the function has to be defined near the number a, but not necessarily at a itself. All right, and so what we would say is if the values of x as they get closer and closer to a, when we plug them into the function f of x and get the y values, right, that those y values get closer and closer to the number L. Okay, so the values of f of x can be made as close as we like to this number L by taking values of x that are very, very close to a, except possibly at the number a itself. Okay. All right, so that's the informal definition. So just kind of looking at what that would look like, or an example, or first example, we have the function f of x equals x squared, and we're taking the limit as x goes to 3 of that function x squared. So what we would do to do this numerically, right, is to imagine taking some values of x that are fairly close to 3 and then plugging them into this function x squared and seeing what the values, the y values, are getting closer and closer to. All right, so I'm going to pick a number that is fairly close to 3.1, right? That's pretty close. In fact, I'm going to have to redraw this table here. This is just not going to work out. So let me make a little bit more room right here. Okay, and so these numbers, the x's, we're going to choose these x's so they get closer and closer to 3, but not actually equaling 3, right? And we are going to plug those in to the function. So starting with 3.1, I'm going to plug that in, right? Remember, our function f of x equals x is x squared, this function right here. So we're going to plug that in and see what we get. So when we do that, we get 3.1 squared, and that is going to come out to be 9.61, right? So that's what the value I get here, 9.61. So that would be the value for f of x for this particular value of x. All right, and then next up, I am going to pick a value of x that is a little closer to 3. So 3.01, I'm going to plug that in to the function and see what I get. And so I'm going to get 3.01 squared, and I already have that calculated out off screen. So that's 9.0601. All right. And basically, I'm just going to repeat that process. I'm going to keep moving this value of x closer and closer to 3. And I'm going to plug those in to the function and get the y value. All right, and that is 9.006001. And you can kind of see the pattern that's occurring right here. So I'm going to take a number that's even closer and plug that in, and when I do that, you're going to get, just like I did the ones before, you're going to get a value that looks like this. And one more time, Now, when you plug that into f of x, you are going to get a value that looks like so. Okay. All right, and so these values of x are getting closer and closer to 3, and so what we would do is kind of look at these y values and see, what they are getting closer and closer to, and it definitely looks like these numbers are getting closer and closer to 9. Okay. One thing that people will ask a lot is, well, how do I know what numbers to pick here? Does it matter what numbers I pick for these x values when I plug them in? If I picked some different x values, could I possibly get a different answer than 9? And for this problem, the answer to that is no, but in general, the answer is to that question is, yeah, you could not get a correct answer if you do it this way. And so that's why this method of numerical limits, it's pretty good to show you the idea of what the limit means, but in the long run, it's not really great to be calculating limits like this. If engineers calculated limits like this, and like for a plane or a bridge or a building or something like that, that you really don't want to have fail, then you really wouldn't want that. You would get incorrect results if you did something like that. So, like I said, this is good for getting the idea of what's going on with the limit, but it's really not good in practice. So once we get past like these first couple of sections, we really will not use this method anymore. All right. Another thing about this is these numbers have to get closer and closer, right, to 3. We'll learn that really later on that if you're talking about 3 on a number line, if you just imagine the number 3 on the number line and the numbers are getting closer and closer on a number line, those numbers are either on the right or on the left of the number line. Okay. So when we're talking about numbers that are getting closer and closer to 3, there's kind of 2 directions that you can get closer and closer to 3 from the right. So if you notice, all of these numbers that I picked are getting closer and closer to the right. So also one of the things you're going to need to do, and we'll make this go into more detail about this later, is also look at these values from the other direction as well. So I could take some values of x that get closer, that are pretty close to 3, but over here on the left side, so they would be less than 3, so like 2.9, and I can plug that in to the function and see what I get. So if I do that, I get 2.9 squared, and I get let's see, 8.41 when I do that. So that number would go here. All right, and then 2.99. 2.99 is a little closer to 3, right? But still, say, over on the left-hand side. So you would plug that in to the function and see what you get. So I get 8.9401. And next I would pick a value of x that's even closer to 3 and plug that in to the function. So that would be 2.999 squared. So that would be 8.99401. And do one more because I'm running out of room. And that's going to give me 8.999 9994001 when I do that. Okay, so these values of x are getting closer and closer to 3, right? And I plug them in, and then I'm looking at these values and saying, hey, are these numbers getting closer and closer to one single specific number? And the answer here is yes, right? If we follow the same pattern, we can see that these numbers are also getting closer and closer to 9. So if you think about it, that meets the definition of the limit. What we would say is the limit as x goes to 3 of the function x squared equals 9. So if we take values of x that are getting closer and closer to 3 and plug them in to this function, the y values that we get out will be getting closer and closer to 9. Okay, so that is what it means to say limit as x goes to a of some function is the number L. All right. And so in this first example, it's a pretty simple function, and for the first example, you kind of want to keep it simple. But a lot of people's reaction when they see this first example is like, yeah, so what? I could just plug a 3 in here. If I plugged in 3, I get 3 squared, which is 9. So what's the big deal of why are you doing all this stuff? What's the point of it? The point is, right, and you might wonder, can I just do that all the time? And the answer is no, you cannot. It doesn't always work out like that. On a lot of problems, it might do that. For instance, if this is any polynomial, you actually can do it that way. And that's not really the interesting part of this. The interesting part is when this number is not even in the domain of this function. In other words, say you plugged in a number and you got a division by 0 or some other strange issue like that. The limit can still tell you some things about what goes on with the function as it gets closer and closer to that point where that's not in the domain. Okay, and that actually is where it actually starts to get useful and interesting, and you'll see some of that in these next examples. So it's not quite as easy as you just always plug this in and you always get the answer. No, that doesn't happen. And so later on in, not in lesson 1B, but in lesson 1C, we'll start talking about what you need to do when that doesn't work out. Okay. All right. That is it on this example.